Yeah. So good afternoon, everyone. Welcome to this edition of the NITheCS Mini-school. My name is Francesco Petruccione, and I'm the interim director of NITheCS. Yeah. This March Mini-school is devoted to, sorry, load shedding just kicked in, is devoted to introduction to solitons and solitary waves in physics and mathematics. And for the 4 lectures, we have a team of 4 lecturers. Last week, Professor Boris Malomet gave us an introduction to multidimensional solitons. And today, here he comes. Yeah. And today we have Professor Sergei Dimitriev from the Russian Academy of Sciences, and his talk will be about spatially localized and delocalized nonlinear vibration in the lattices. Yeah. And one of the team members that delivers this mini-school, Dr. Daniel Sadapman, knows Professor Dimitriev very well, and I will ask him now to briefly introduce to you.
I'm still not sure about that.
And
good
Daniel,
afternoon,
please.
everyone. It is great, my pleasure to introduce Professor Sergei Dimitriev. Professor Sergei Dimitriev graduated from the Tomsk State University in Russia. He has completed his master in 1984, and after that, he's got his PhD from the Tver State University in Russia in 1988. And he moved to Japan, and he's got his second PhD in computer modeling of phases in dielectrics from University of Electrocommunications. And he received a habilitation degree in 2008 with the thesis on solitary waves dynamics in discrete system from Altai State Technical University. Since 2008, Professor Dimitriev has been serving the head of laboratory of Institute of Superplasticity Problems of Russian Academy of Science in Ufa. Professor Dimitriev, you're more than welcome to give a talk for us. Thank you very much for accepting our invitation. Thank you.
Yeah, it's my great pleasure to deliver the results of our recent studies, and I'm very grateful to Daniel for inviting me, and to Francesco who takes care of these meetings. So thank you very much. One day I wish to visit South Africa. Hopefully,
we will be very happy to make a plan.
Yeah. Okay, so let me start. I will talk about nonlinear dynamics of lattices, and the scope. Okay, of my talk is presented here. First, I will just introduce terminology, what we call lattice, what is nonlinearity. Then I will firstly introduce spatially localized vibrational modes. They are called discrete breathers, or equally intrinsic localized modes, but I will use the shorter term discrete breathers. Then I will introduce you delocalized nonlinear vibrational modes, and we will discuss their relations. You will see that there is a very strong relation between those spatially localized and delocalized modes. Of course, I will talk about the importance of studying of discrete breathers, and just as immediate introduction, here you can see spatially localized mode called DB, discrete breather, abbreviated as DB, and delocalized nonlinear vibrational mode, DNVM. And maybe you already can see that basically they have same nature, just what we can see in the right for delocalized mode. So even and odd particles vibrate in antiphase, and the same is true for the localized mode. So if we apply bell-shaped function upon delocalized mode, we can get this discrete breather, localized mode. But the carrying function is the same. And this is the main motive of my talk today. So there is a relation between these two creatures. Okay, so first terminology. What is lattice? The field where I am involved to, lattice is any periodic array of particles that interact with each other. And these interaction forces, if they are linear, then the problem is more or less trivial. We can solve linear problems. And the most interesting effects are observed when the force acting between two particles depends non-linearly on the distance between these particles. Then we call such lattice non-linear lattice. And non-linearity brings many new effects that are absent in the linear lattices. For instance, this localization of vibrations is possible only if the lattice is non-linear. I'm talking about perfect lattices, lattices having no defects. Okay, and we say that oscillations of particles are localized if we have exponential decay of their vibration amplitudes away from the center of localization. Okay, so here you can see the images. To the right is the delocalized mode, and to the left is spatially localized mode, which was obtained by applying bell-shaped function upon the delocalized mode. Okay, so first of all about the discovery of discrete breathers. So they were discovered by Dolgov, and he published his result in Soviet journal, Physics of the Solid State. And this work was not noticed by the community. And 2 years later, independently, Sivers and Tekena have rediscovered discrete breathers. And then many other mathematically oriented scientists did their great works to understand the sense of discrete breathers. You can see the two review articles, Flach-Willis and Flach-Gorbach, and our paper published about discrete breathers, particularly in crystals, because what we are interested in are actually crystals. But the basic physical phenomena have been found and described very well using very simple models, like the model you can see here. It's just a chain of particles, one-dimensional model of crystal. You can see here the Hamiltonian, which is the sum of the kinetic and potential energies in the system. And potential energy has contributions from the interparticle bonds. They are nonlinear. As you can see, they are presented by the polynomial function with up to 4th order. And there is also on-site potential here. I'm sorry. I must switch. Okay, for any we start our analysis usually from studying linear systems. So we neglect all the anharmonic terms. We obtain linear lattice, and we can find the dispersion relation for small amplitude waves propagating through this lattice. You can see it is called here phonon spectrum. And in discrete lattice, phonon spectrum is always limited from above. So we have maximal phonon frequency, which corresponds to the shortest wavelengths. However, in continuum lattice, suppose this is not a discrete lattice, but a continuum rubber-like elastic media, then the dispersion relation would be a straight line, which increases up to infinity. And in this case, the spectrum is unbounded. For us, it is very important that spectrum is bounded from above. As you can see here, the image of discrete breather, we must answer the question, why energy stays localized? Why it doesn't spread over all lattice? And the answer is very simple. Vibration frequency of discrete breather is above the phonon spectrum. So discrete breather does not interact with any small amplitude wave, does not excite such waves, and doesn't lose its energy for excitation of propagating small amplitude waves. And that is why it remains ideally forever in the lattice. Okay, so now we know that we can get this type of energy localization only in discrete lattice, where the phonon spectrum is bounded from above, because we must have frequency, vibration frequency above the phonon spectrum. And the second question is how frequency can be above the phonon spectrum, why it can be so. And the answer is this happens due to nonlinearity. Let me show you, I think. This happens because of nonlinearity. Nonlinearity is the second very important ingredient when we want to obtain discrete breathers. First is discreteness, and second is nonlinearity. Okay, here you can see 1 degree of freedom oscillator. It is just mass m suspended on the spring, which is characterized by 2 constants. K is the elastic constant, linear elastic constant, and beta takes into account the nonlinearity of this spring. Equation of motion, you can see here, the second order differential equation, and using this substitution with the first and third harmonics, we can obtain approximate relation between frequency and amplitude. What we get from this relation? Omega square, and you can see the equation. Suppose we neglect unharmonicity. We set beta equal to 0, so we remove the cubic term. Then immediately we can see that omega becomes constant, which does not depend on the amplitude. So omega square will be just k over m, which are the constants. So this is depicted in this graph. You can see that omega for beta equal to 0 does not depend on amplitude. However, if we consider nonlinear spring, then we have 2 possibilities. Beta negative, then frequency will decrease with the amplitude, or beta positive, then frequency will increase with the amplitude. And now we understand why nonlinearity is so important. If we want to be above the phonon spectrum, we can rely on nonlinearity. With increasing amplitude, frequency will grow and can leave phonon spectrum, or can split from the upper edge of the phonon spectrum. And we can enjoy this energy localization. So I conclude that if we want to obtain in a lattice spatially localized vibrations, discrete breathers, then we need 2 major ingredients. This is discreteness to make the phonon spectrum bounded, and we need nonlinearity. Due to nonlinearity, frequency shifts with the amplitude, it can leave the phonon spectrum. Okay, in crystals, actually, we can consider monatomic crystal or biatomic crystal. In monatomic crystal, spectrum is usually does not have any gaps. You see, it starts from 0 and, as in this case, grows up to 10 terahertz, something like that. However, for biatomic crystal, if we have different atom masses for light and dark atoms, then phonon spectrum can have this gap. So we have low frequency band and high frequency band. High frequency band is for light particles. We can see that if mass is small, then frequency is high. So light particles vibrate at high frequencies and they make their own band, which is separated by this gap from the low frequency band. Okay, and now let us talk about discrete breathers. We already know that discrete breathers frequency must be outside the phonon band. And in the case of monoatomic crystal, we have only one possibility. Discrete breather frequency must grow with amplitude and leave the phonon spectrum being above the phonon spectrum. This type of nonlinearity we call hard type nonlinearity. However, when we have a gap, we have three possibilities to have discrete breathers, as depicted here. Two with the hard type nonlinearity, and blue line shows discrete breather with the soft type nonlinearity. And actually, in crystals, all types of these discrete breathers can be observed, can be found. Okay, here I would like to show you some experimental works where people create handmade lattices and study energy localization. So this is mass spring chain, microcantilever array, and many others, and even two-dimensional model. Here, magnets, two-dimensional lattice of magnets that interact with each other through this repulsive potential. Also, you can enjoy study localization of energy. Okay, and this slide shows that actually discrete breathers have been described in all types of crystals, in ionic crystal, sodium iodide, also in covalent crystals like chromium, germanium, diamond, in ordered alloys, in pure metals with all possible lattices, and also in two-dimensional nanomaterials. So mainly this work was done using molecular dynamics simulations, but there are some experimental works on discrete breathers in crystals. The results are debated, so today maybe the most important method for studying discrete breathers in crystals actually is numerical simulation. Okay. Now let me turn to delocalized nonlinear vibrational modes. You can see example of delocalized mode here in one-dimensional chain, and two modes are shown in the lattice of graphene, hexagonal lattice. Actually, such modes have been known long ago, but a rigorous approach and very fundamental works can be found in the papers which I cite here by Sakhnenko and Chechin. They have done great work showing that any lattice supports such modes that can be found considering only symmetry of the lattice. So when you derive such modes, you do not assume any interparticle interactions. You derive them just considering symmetry of the lattice. That is why such solutions exist as exact solutions for any given lattice, regardless the type of interaction between particles and for any amplitude. So they exist as exact solutions for large amplitudes as well. But since we are doing nonlinear physics, for us it is important that just considering symmetry of the lattice, we can find a number of exact solutions to the nonlinear system. Okay. Also, I would like to introduce you a very important discovery, which links the delocalized modes and discrete breathers. This discovery was made by Burlakov, Kiselyov, and Trupasov, and later studied in many, many works. It is emergence of discrete breathers, highly localized discrete breathers, as a result of modulational instability of delocalized mode. What did they do? They have excited the delocalized mode in the chain of particles, as you can see here. So you just shift odd particles to the right and even particles to the left, release them, and they start vibrate like this. However, this vibration is modulationally unstable, and the development of this instability brings us very interesting results. Let us see how the energy distribution in the lattice changes with time. Initial state is shown here at the bottom, and due to symmetry of the mode, each particle initially has the same energy. So all of them share energy of the system equally. However, development of modulation and instability begins with the appearance of this sinusoidal modulation of energy. And it doesn't stop here. Eventually, we have in the system highly localized vibrational modes, discrete breathers. Discrete breather has very long lifetime, but it radiates energy slowly, and eventually we come to thermal equilibrium. So you see that development of modulational instability of delocalized mode gave us discrete breather. Discrete breathers in this case are called chaotic discrete breathers. I don't know, just this term is widely used, maybe just because we don't know where and how many discrete breathers will appear, because this is more or less a random process. But anyway, this is a very, how to say, general phenomenon. Okay. Similar, then delocalized nonlinear modes can be found for any lattice. Here you can see 16 modes found for square lattice. The question is, how do they differ? First of all, they differ by the frequency amplitude relation. Do I have them here? Okay, and for us, most interesting modes are those whose frequency is above the phonon spectrum. And we have checked all these modes and found that only first one and the last one, this one, they have frequencies above the phonon spectrum, as it is shown here. You see, the upper edge of the phonon spectrum is shown by the dashed line, and these two modes, now they are called DNVM1 and DNVM2, they have frequencies growing with amplitude and bifurcating from the upper edge of the phonon spectrum. Okay, we can study modulational instability of these two modes, and we will get exactly the same result, qualitatively same result, which was described by Burlakov and others, and in many other works. So this is shown only a small part of the lattice. Here we have many particles in the computational cell. We excite this mode, and we can see that first, sinusoidal kind of sinusoidal modulation appears. Energy becomes not equally shared between particles, and this process then results in the excitation of highly localized discrete breathers. These dark dots are discrete breathers. So energy is highly localized, similar to what we had here. You see here, sinusoidal modulation transforms to a highly localized discrete breather. Same is here. Of course, this mode behaves similarly. It also produces discrete breathers. Why we have discrete breathers? Why energy is localized? The explanation is very simple. You see, since frequency of delocalized mode is above the phonon spectrum, it does not resonate with any extended phonon, and it cannot give energy to any delocalized phonon. So the system must go through energy localization, and these discrete breathers have very long lifetime. They eventually disappear, and system eventually will come to thermal equilibrium, but the lifetime of discrete breathers is really long. So we have this very interesting phenomenon. Okay. I have already shown you that actually by applying localizing function upon delocalized mode with frequency above the phonon spectrum, we can get discrete breathers. Here you can see examples of one-dimensional discrete breathers in square lattice, and they were obtained by applying this localizing function. You see, localization goes only in the vertical direction, while in horizontal direction, it stays delocalized. But anyway, we call this discrete breather, because here we do have spatial localization of particle vibrations. Red line shows where is the center of localization. So the localization function is organized as follows. Beta is a parameter of localization, and Dij are the distances of particles from this line. You choose a line. Of course, it should be a line going along a high symmetry direction, like this, over one closed spectral row, or like this in between two closed spectral rows. And by choosing this parameter of localization beta, we can obtain such discrete breathers. Also, we can get zero-dimensional discrete breathers. Now they are localized in both directions, and we choose two lines, orthogonal lines, and we put the center of localization in different points, and we get different discrete breathers. Also, the second mode also produces discrete breathers that can be found one-dimensional or zero-dimensional. So let me conclude that actually what we have here, we have a general approach of finding discrete breathers in complex lattices, in multi-dimensional lattices, in two-dimensional and three-dimensional lattices. How do we start? We start from the analysis of symmetry of the lattice and find all delocalized modes, as we did, for instance, here for square lattice. We have found all delocalized modes. Then we calculate frequency amplitude dependencies of these modes and take those that have frequency outside the phonon band, because discrete breather has frequency outside the phonon band, and we must get the non-resonance condition. And then we apply localizing functions, as I have shown you. And this approach is general, can be applied for any lattice, three-dimensional, two-dimensional, any lattices. And you can get a number of discrete breathers, not just one. And we know that actually all discrete breathers described in the literature, as we know, they are related to a delocalized mode. So there are no discrete breathers not related to a delocalized mode. So the correct way of studying discrete breathers is to start from the analysis of delocalized modes. Okay, now I would like to tell you, you see, during the development of modulational instability, we can calculate this localization parameter. Here, En is the energy of nth particle. So in the numerator, you sum squares of energies, and in the denominator, you square the sum of energies. And if energy is localized, spatially, this parameter will tell you that it is so. So here you can see how parameter L, the localization parameter, changes in time during the development of modulational instability of delocalized mode. First, when mode is still vibrating as it was excited, localization parameter is very small. Then sinusoidal modulation appears and discrete breathers start to appear in the system, and localization parameter increases sharply. Then discrete breathers live for a very long time, but they gradually radiate energy and eventually disappear. So during this transformation, during this flow of energy in the system, we can calculate various macroscopic properties like thermal expansion of the lattice, heat capacity. We can calculate elastic constant of the lattice. And we see that all of them do change when we have discrete breathers in the system as compared to when the system comes to thermal equilibrium. From these experiments, we can find how discrete breathers affect macroscopic properties of crystals, macroscopic properties that can be measured in the experiment for lattices, for crystals, for real crystals. So this is just to tell you that discrete breathers do affect properties of crystals. That is why the study of discrete breathers is very important for the solid state physics. And one more application of delocalized modes. These are the delocalized modes found from the consideration of symmetry of body-centered cubic lattice. So this is three-dimensional lattice. And here we have calculated frequency amplitude relations for those modes using ab initio simulations. Ab initio simulations are believed to be exact ones since they take into account electronic structure of the system. However, this type of simulation is possible only for small computational cells, like in this case, we can do it. But we cannot do it for millions of atoms to study dislocation dynamics or plastic deformation of atoms. We must rely on molecular dynamics. And molecular dynamics uses the phenomenological interatomic potentials. And the accuracy of these potentials is debated, and it is not easy to answer the question which potential is better. However, using these frequency amplitude dependencies for these modes, we do have a method of estimation of the accuracy of the potentials. You see, here open circles show the results of ab initio simulations, taking into account electronic structure. And other curves, other lines, show you molecular dynamic simulation results obtained using different interatomic potentials. We have calculated it for all modes, and you can see that some of the potentials reproduce frequency amplitude dependence nicely, but others are not good. So now we have method of estimation of the accuracy of the potentials for large vibration amplitudes. This is important. Okay, so I conclude my talk by saying that nonlinear lattices support delocalized modes as exact solutions that can be found considering only lattice symmetry. And those delocalized modes that have frequencies outside the phonon band are very interesting for search for discrete breathers, because applying localization functions, you can find new types of discrete breathers, or observing modulational instability of such modes, you can see the chaotic discrete breathers. And the last point is that discrete breathers do affect macroscopic properties of crystals. That is why it is important to study the effect on the macroscopic properties. And this is indeed a very important part of the solid state physics. So thank you very much for your attention. And if some questions, surely I would like to answer.
Thank you very much. Can you hear me?
Yes.
Thank you very much, Sergey Dmitry. As a participant, I really enjoyed your presentation.
Oh, thank you
very much.
Thank you.
I can see a question, Sergey asking, your consideration is still classic. What about quantum effects? Do they change anything?
Quantum effects do not change anything, because, as I have mentioned, delocalized modes are derived by considering only lattice symmetry. And it doesn't matter what kind of interaction is between particles, these modes are exact solutions. For discrete breathers as well, we have done ab initio simulations, they also called first principle simulations for some crystals, and actually basic physics works. So if vibration frequency of the mode is outside the phonon band, it can stay localized. It doesn't matter what kind of interparticle interactions you consider. Is it just molecular dynamics phenomenological potential, or you take into account electronic structure? It doesn't really matter.
Okay, thank you. Another participant asked you a question about, I want to know if all nonlinear systems can support delocalized modes.
Yeah, systems with translational symmetry, they do support delocalized modes. Yes, yes, a number of them.
Okay.
Several families, different families, because they are found by considering using the group theory, considering groups of crystallographic symmetry of lattices. So this is very well known science. All those groups are tabulated. You can find them in textbooks. You just apply those symmetry groups, and for any lattice, for any periodic system, you can find delocalized modes.
Okay, thank you. Another person who has a question, I guess, Professor Weigel. You are more than welcome to ask your question, Professor.
Yeah, okay, so I've just unmuted my microphone. Thanks for the interesting talk. Actually, I have two questions. I think one is just very short. The first one. So at the beginning, you mentioned as one characteristic that the localized breathers would somehow decay exponentially along the lattice. So did you check that, or do you also allow for a power law decay, or must it really be exponential?
Mm-hmm. Actually, this is the result of linear analysis. In the tails, vibration amplitudes are small, and for small vibration amplitudes, linear theory does work. And linear theory says us that it must be exponential.
Okay.
But I believe that in some very tricky cases, there are some works on compact tones and other stuff, very unusual type of interaction. Maybe yes, but in real world, in the crystals, I believe they all are exponentially localized. Mm-hmm. Thank you for your question.
Okay. So yeah, one other question I actually have is, can you let me say following. So, is it possible to construct a wave packet from ordinary oscillations and have it scatter of a localized breather?
I think I didn't get you. Could you please repeat somehow?
Okay, so let's assume you build a wave packet from ordinary oscillations. So they have those which have the standard dispersion relation.
Okay.
Okay. So and they have wave numbers or wavelength longer than in the distance between two lattice sites.
Yeah.
Okay. So I can build a wave packet from that, and then you give that wave packet an initial velocity towards a breather.
Okay.
Okay.
Yeah.
And can you simulate such scenarios and eventually calculate some scattering, or let's say extract some scattering data from that?
Yes. It's a very interesting question, which has very important application in the theory of thermal conductivity, because there are some works that say that thermally populated discrete breathers, they do reduce thermal conductivity by scattering phonons.
Okay.
So yes, indeed, this is a very important problem, the study of interaction of wave packets with discrete breathers. Wave packets, as I guess you mean, they have not very high amplitude, but discrete breathers, they are high amplitude creatures. And in thermal equilibrium, there is always some probability to find a discrete breather with high amplitude. And of course, this discrete breather would scatter phonons and contribute to the reduction of thermal conductivity. Yes.
Okay, that sounds interesting. Thank you.
Thank you.
Okay, thank you very much. I think Professor Malumet also has a question.
Yeah, привет, Sergey. Nice to see you here.
Yes,
okay.
Very nice.
The question is, do you have examples of discrete breathers which simultaneously develop chaotic internal oscillations but keep the self-trapped, that is localized structure, do not decay while demonstrating internal chaotic dynamics?
Well, discrete breathers, we call them actually, those discrete breathers that I have described here, they most likely, they are not exact discrete breathers. We call them quasi-breathers. Why? Because otherwise we have to find the rigorous proof, but we are not mathematicians and we don't know how to do this. We call them quasi-breathers. And actually, there is a nice work by Chechen who introduced quasi-breathers by saying that, well, exact discrete breather is single frequency vibrational mode, but quasi-breathers, they have kind of other harmonics, and those harmonics are not strong, but anyway, they are present. They result in some leak of energy away from the discrete breather. So actually what we claim that we find long-lived large amplitude oscillatory modes. Indeed, they radiate energy very slowly, extremely slowly. Actually, we cannot reach their lifetime in our numerical simulations. But they are not all of them are perfect. So some of them has some internal life. I don't know how to, is it what you mean? Or maybe—
No, I actually asked a different question. Okay, I understand that this dynamical modes are not truly localized because there is very weak decay, very weak leakage of radiation. But as long as they stay practically localized, so as long as you can neglect the radiation loss, is it possible that simultaneously they develop internal chaotic dynamics? That the oscillations are not regular, not just quasi-harmonic or anharmonic, but are chaotic?
I don't know. I don't know answer to your question. Never thought this direction. Sorry, Boris. Maybe you can give me a hint, or I have no idea why you ask this question. Even this puzzles me. Because, well, we look at discrete breathers as, well, quasi-periodic vibrational modes, but chaotic. In what sense chaotic? I don't know. What do you mean?
Chaotic that they develop just as in the sense of the theory of nonlinear oscillations. Nonlinear oscillations may become chaotic.
Well, I must think. Thank you for your question. It's
okay. Thank you.
Yeah.
Okay, thank you very much for your question. I think another people also have a question. Let me ask one by one. Delocalized nonlinear wave modes has a frequency outside the phonon band. If it is the case, can we say that nonlinear supra-transmission phenomena is similar to delocalized nonlinear wave modes?
Oh, Daniel, please read once again. It's a long question.
Okay. DNVM has frequency outside the phonon band.
Yes, yes.
If it is the case, can we say the nonlinear supra-transmission phenomena is similar to DNVM?
First of all, not all of DNVMs, and actually a few of them have frequency outside the phonon band. Many of them have frequencies within the phonon band. Well, this is first what I would like to say. But let us talk about those which have frequencies outside the phonon band. So supratransmission means that we apply external force at the frequency outside the phonon band, and we can see excitation of delocalized mode. Yes, I think here we have the relation as mentioned in this question. So by applying periodic external force at frequency above the phonon spectrum, we indeed have something what can be called supratransmission. Yes, I think so. But the amplitude should be sufficiently large, as it's a condition for supratransmission. If amplitude is small, no supratransmission. When we apply sufficiently large amplitude, we do have it. Yes, thank you for the question.
Okay, thank you. Another question is that what are the typical energies of interatomic oscillation in a crystal you consider? It says that I'm asking in connection of possible penetration through the barrier between two nuclei and pairs.
Again, I didn't get.
What are typical energies of atomic oscillation.
Yeah. Okay. Typical energies of discrete breathers, right?
Yeah.
Usually it is a few electron volts, up to 10 electron volt, let's say. So we cannot say tenths of electron volt, but up to 10, no problem. You can pump energy up to 10 electron volt into a discrete breather in metals or in covalent crystals, something like that. And this energy can travel through the crystal. I didn't talk about moving discrete breathers, but many of them can move, can propagate, and can carry energy in localized form through the lattice. So this is another important property of them, which contributes to some physics in solid state physics. Yes.
Okay, thank you very much. As I can see, there are no more questions at the moment. I would like to thank you again for accepting our invitation to give a talk for us. And
thank you very much.
Thank you for everybody to take a part in this lecture. Hope to see you everybody in the next week at the same time. Thank you very much.
Thank you,
Thank you.
everybody.
Bye-bye. Bye.